Right, so we're working through some trigonometry at the moment. We've been doing some trig identities, some double angle identities, all heaps of fun. Having a great time with this, but it gets more interesting probably as we look on now towards exercise 13F and looking at some more. Now that we've got these double angle results, we can solve more equations. So we'll have a look at a couple of examples in a minute. On the screen at the moment, these 1, 2, 3, 4 questions here, these are past exam paper questions. I'd like you to have a go at these. So they're on your screen now. Take a screenshot of it or whatever. Copy them into your book. Have a go at them. I'm going to leave that for a day or two, just to give you a chance to have a go at those, and then I'll post the solutions. Okay, let's have a just look at some more examples then. So I'll just scroll down the page here. That might not have been on the page, that last little bit there. Hence, solve the equation. So if you need to, just have a pause and write that down. So looking at the examples now on page 460, 461. So I'm just taking straight from there. So an example now here is solve sine 2x equals sine x for x between 0 degrees and 360 degrees. Okay, so that's right. These brackets around the 2x, I guess they're important because without the brackets, you'd probably still think of that as sine 2x, but in effect it could be sine 2 times x. So the brackets are just making it clear what's going on there. All right, so this is an equation for us to solve. What are we going to use here? We're going to use the double angle result for sine, which is again, I'll just point out again, if you want to solve this, a good idea to solve this yourself. Pause the screencast, do it, and then press play and check your solution. Get some immediate feedback, which is perfect. 2 sine x cos x is sine 2x. We're relating, remember our double angle results, just relate all our double angles back to single angle results, which for us are much easier for us to find given clues that we're given. So 2 sine x cos x equals sine x. Temptation here might be to divide by sine x and get rid of them. Dangerous, because sine x could be equal to 0, which is actually a solution, isn't it? If you make sine x equal to 0, you get 0 equals 0. And you would be ignoring some solutions that way. So don't do that. Rather, factorize. So 2 sine x cos x minus sine x equals 0. So get 0, clear the right side so you get 0. Left side needs factorizing. So this is a good example of an algebraic solution where you could be tempted to divide through by something and remove it. But when you do so, you remove that what you're dividing by. If that equals 0, if that is a solution, you're ignoring it by dividing through by it. Because remember, when you divide through by something, you're assuming it's not equal to 0. You can't divide by 0. So sine x, I'll show you, it'll come out in a second. 2 cos x minus 1 equals 0. So you can see here what is in brackets. We would have got that result just in brackets if we divided through by sine x. But without doing so, and with just factorizing, we have a look at sine x equals 0. So we're going to consider that as a solution, and cos x is equal to 1/2. So there's my two channels of solutions. Sine x equals 0. Now let's have a look here. Sine x equals 0. That's where the y coordinate is equal to 0. On the unit circle, so that's the y coordinate is equal to 0 there, and it's equal to 0 there. We're going from 0 to 360, so we can say therefore that x is equal to 0, 180, or 360 degrees from sine x equals 0. Cos x equals 1/2. All right, so what's going to help us here is that little half triangle there, where that's 2, that's 1, and that's root 3. I'll just blow that up a little bit for you. Cos x equals 1/2 is that angle in there, and that angle in there is equal to, in degrees mode, is equal to 60 degrees. Alright, so shrink it back and finish this solution off. So cos x equals 1/2, it's a 60 degree, and oh yeah, we're also in the quadrants where cos is positive there and there. So the 60-degree angle in there, alright, that one there is 60, and the 60-degree angle in here is that one there, which is 300. So from this solution we get x equal to 60 degrees or 300 degrees, and what is customary now to rewrite our solution in ascending order, picking up all the solutions. So 0 degrees, 60 degrees, 180 degrees, 300 degrees, and 360 degrees. So 1, 2, 3, 4, 5 solutions to that equation. Okay, picking up the second example, which is a prove that. Alright, this really is for the purists, for the diehards, for the trig lovers. Prove that 1 plus tan squared theta, no, it's tan squared x. Let's get that right. 1 plus tan squared x cos 2x. Okay, now that is that's in brackets there, so it's that times cos 2x equals, that's in brackets, equals 1 minus tan squared x. Okay, so what I like to do here is work with the left-hand side and arrive at the right-hand side. That's the solution in the textbook works with both sides and produces a common, a well-known identity, and therefore it's proved. I prefer to work with the left-hand side, so I'm going to do that, and then I arrive at the right-hand side, as you'll see here. So the method here, I think, can be a little confusing, but if you start with the left-hand side, LHS, left-hand side, I'm now going to rewrite this out. 1 minus tan squared x times cos 2x. I'm going to rewrite it as 1 plus, well, I'll keep tan at the moment. I might need to change that to sine squared on cos squared. Cos 2x is cos squared x minus sine squared x, among other things, but we'll see if that helps us. Remember, we're trying to expand this out to look like this. Alright, so there, which equals cos squared x, when we just do this expansion, minus sine squared x. Now this here, tan squared times cos squared, if you imagine that as sine squared on cos squared times cos squared, that gives us sine squared x. And then tan squared times sine squared is sine on cos times, so sine squared on cos squared times sine squared is minus, it'll be sine 4x over cos squared x. Okay, so that's that expansion. Remember, for those last two, I've written tan squared as sine squared over cos squared. I've got that in my head, and I'm doing that. Perhaps I'm now considering whether I need to show you the working out for that. So let's just do that quickly. So this tan squared times cos squared, that one there, tan squared, that one is sine squared x over cos squared x times cos squared x over 1. So they cancel, and you're just left with sine squared x there. Now the other one I just did was tan squared times sine squared, and if you look at that over here, tan squared is sine squared x over cos squared x, times that by minus sine squared x over 1. Play that up. Then no simplifying, it's minus sine 4x over cos squared x. And you can see I've written that there. Okay, so continuing now with this, cos squared x minus sine squared x plus sine squared x. So those two terms there cancel each other out. So we're just left with cos squared x minus sine 4x over cos squared x. What I'd like to do here is multiply through by cos squared x. Can't really do that. Pause. And resuming now, so we've got cos squared x minus this fraction here. Now I figure that this can be factorized like so. Cos squared x 1 minus sine to the power 4x over cos to the power 4x. If you run that through, you'll see that's all good. We then have pause. Okay, I now see this as a difference of two squares in the brackets here. So that's 1 plus sine squared x over cos squared x, and 1 minus sine squared x over cos squared x. Okay, so what we can do now is expand this bracket here to get cos squared x. Now cos squared times sine squared on cos squared is sine squared. So I get that by, and this is 1 minus tan squared x. Now this cos squared plus sine x is 1 by 1 minus tan squared x, which equals right hand side. We just put that there and our job is done. Now that is the beauty of these questions is that there's lots of different ways of doing them. You'll see another example in the book that also works. And there was also probably one or two other things I could have done through this process that could have led to that. Now they're not all this difficult, but that's the idea of them, is that you start with the left hand side and you try and change them around using the identities that we've come up with, that are there at our disposal. Rewrite the expression so that we get it looking like the right hand side. Okay, that's enough from me. I'll see you on Thursday.